So I am going to talk about filtering potential field data, and it's something that I actually really enjoy doing. At Fathom, we do a whole range of things, from survey planning, data QC, data filtering, interpretation, targeting, drill target definition. But the aspect of the work that I enjoy the most is actually filtering the data. So I have put together I'm just going to try. There we go. It's having a few technical difficulties before you all joined, and my screen just froze again, Helen, but we're back on track. So I actually have some data to show you, and I've just got a few slides before we look at any data, just to go through a few key points. And I think anytime you're using potential field data, so anytime you're using magnetic and gravity data, it's really good to keep a few points in mind. Probably the most important point is that all you're doing is looking at a map of different physical properties of the Earth. And so if you're looking at magnetic data, you're looking at changes in magnetic susceptibility. You're basically looking at which parts of the Earth have a lot and not much magnetite. And if you're looking at a gravity map, you're basically looking at changes in density. And we are fortunate in that the rock types that we have and that we are looking at for mineral exploration, they most often have different densities or magnetic susceptibility. So we can map the changes and we can use those changes to understand both the framework and to look for specific targets that we may want to drill. There are really two applications of potential field filtering. We are either trying to map, so either trying to understand the distribution of rocks and properties, or we are trying to directly detect something of interest. And when we're using direct detection, actually you can use magnetic. Often it's electromagnetic data that you would fly and model to directly detect or define a drill target. But you can also have a magnetic response that is quite discrete and particular. So a cyanide gold deposit has a discrete magnetic response. More recently, the Havieron deposit in WA is a distinct magnetic blob. So you can use magnetic data for direct detection. And certainly gravity data, if you collected it at a high resolution, you could directly detect a nice dense VMS deposit. So, but generally, we're using magnetic and gravity data to actually to look through the Earth and define the framework. What is our structural regime? What directions do we see? Where are the intersections? What sort of distribution of units do we have? So, move the heads. Like I said earlier, we're relying on there being a contrast in a physical property for the methods to exist. Now, I really like this example. It's Excalibur's promo PDF on using airborne gravity gradiometry data in Victoria. And you can see on the right that we've got the magnetic data, and on the left, we've got the gravity data. There's just nothing in the magnetic data at all. There are no contrasts in susceptibility in these particular sedimentary units. So you do need to be aware of what sort of contrasts you would expect, and then you need to collect the appropriate data so that you can map out those contrasts. And ultimately, what we're trying to do using both magnetic and gravity data is to actually reduce the amount of Earth that we consider prospective for whatever we're looking at. And if we can do that, if we can actually reduce the amount of Earth down to half of our tenement just by interpreting magnetic and gravity data and defining the structural setting, then we're using that data effectively. But ultimately, there is no silver bullet. You do need to use as many data sets as you can together, integrate them, force them to make sense relative to one another to actually really understand what's going on. And like I always say to my clients, spend time, get to know your data. You can't be using filtered geophysical data occasionally in a sort of, you need to focus, sit down, give yourself the time and really, get to know your data. All right, I'm going to move through this pretty quickly, but if you really want a good book on geophysics, just go and get Mike Denteith's book. I've stolen a lot of schematics from that book. Yeah, this is my favourite one. For mineral exploration, and actually for potential field data, what we need and what we want is not flat-lying stratigraphy like this on the left. That whole sedimentary basin patrolling setting is not ideal for potential field data. It's great for seismic, but not for mag and gravity. What we want is the picture that we have in the middle, where we have vertical, subvertical, steeply dipping units with nice lateral changes, so we can really detect differences between the different units. And then in a perfect world, the figure on the right, included in that earth would be some discrete body full of excellent, full of mineralization that we can sell, that has a different physical property to the rocks surrounding it. So this is a sort of model on the right that we are ideally hoping to have on our ground and detect using our geophysics. This is another really good presentation that Clive Foss put together. I found it while I was thinking of a few things to say here. Have a look at it, it's brilliant. A few points to note with magnetic and gravity data. I've already said, mentioned the fact that we need lateral changes. There's no point using the techniques if there are no contrasts. But also we can't separate overlying bodies. So down the bottom is an example of, hopefully you can see my cursor. I'm going to get my little fancy laser pointer back. There we go. This scenario gives this gravity response. The scenario on the right gives exactly the same gravity response. So we can estimate what's happening below, but there are certain limitations in terms of our interpretation. But I would say as long as we're aware of those limitations, we can push magnetic and gravity data really far and really understand what's going on. Okay, so the laser pointer stops me changing the slide. All right, today I've only got 45 minutes and I've told Helen to say stop because I could just talk all day. You could actually have a whole week's course on data planning, filtering, interpretation and targeting, but I'm just going to show you a few filtering examples today. And this is the brief that I set myself. So I'm going to show you filters that anyone can use and anyone can apply to data using off-the-shelf software. So nothing specific to Fathom, nothing specific to any other consulting group, just good standard filters that we can all use and know. I've also put examples in that are using Australian public domain data. So it's also data that we can all access. And of course, there's some fantastic public domain data in other countries, particularly Canada and Finland, but I'm sticking to Australia today. The examples that I show are regional scale, but the same idea can be applied to a prospect or tenement scale. I didn't actually end up getting to putting much in about targeting models. We can do another talk on that another day. I won't go through this, but often when I'm presenting filtered products to a client, I will then say, look, go off, get to know your data, enjoy interpreting and targeting, but these are the sort of things that you want to be able to, the questions that you want to answer when you use the filtered products. Potential field data can be manipulated. You can pull out responses that are more likely to be shallow and responses that are more likely to be deep. You can find boundaries, which are always critical. Structure is a part of almost every mineral deposit model and mineral systems model. So you do want to define the boundaries. And then you can do things like trace magnetic linears, map out folds and fold noses, look at the orientations, all sorts of fabulous things. Right. We are looking at the gravity response of Australia. And I love this image because it's big scale. But I think it's always important to look at the regional framework. It doesn't matter where your tenement is, and it doesn't matter where your project is. You need to step back and ideally have a geophysicist produce a set of products for you that just shows your package as a part of the larger whole, because it's really important to know the overarching framework. Where are the big cracks? And also, where are the known deposits in the area and what sort of responses do they have? And you don't need to do that in any super detailed way, just noticing. Let's choose one randomly. Okay, I'm not sure that's not a good example. Looking at which deposits in an area sit on certain structures, what orientation are those structures? Are they on structural intersections? Can you build a story about known deposits and apply that story to the ground that you hold and the data that you've had filtered? So I've got 3 example areas, and let's see if I can get through them all. One point that is important to make, and I said earlier that you can apply what I'm talking about to any scale, and that's true. But there's a difference between what you would use in terms of your deposit model and your mineral systems approach at the camp scale versus the deposit scale. So understanding where the controls are and what you want to pull out of your data at those 2 scales is quite critical. At a camp scale, you can use regional, public domain, freely available data to map out where your controlling structures are, where your cross structures are, where you've got key intersection zones. You can do that across Australia using free data. Once you're at your deposit scale, it's more likely that you'd want higher resolution data because you are probably looking for smaller footprints of smaller responses. And in that scenario, you may be looking for quite discrete magnetic highs if you're looking for cyanites, or let's say you're looking for intrusive related gold. You're going to look for complexity around an intrusion margin. Those sort of features, you'll need more detailed data. And that's the point at which you may consider flying your own. All right, so we're looking, which one have we got first? Oh, we're looking here. Before I actually show you gravity and magnetic data, I just need to give topography data a little pitch, because topography data is often underrated. It's freely available. You can go to OpenTopo and you can download 30-meter resolution, spatial resolution topography data for basically the whole globe, except the very ends. And in some scenarios, less in Australia, but in areas where you've got neotectonics, you've got active tectonics at the moment. So New Zealand, Japan, Southeast Asia, South America, you can process topography data in the same way you process magnetic and gravity data and pull out a lot of really useful information. So don't forget to consider topography. So here's the topography for a little area that we're looking at. I've put no color bar and no scale, which is very naughty, but the brown bits are higher and the blue bits are lower. And here we have the public domain gravity data over the same area. Gravity data is a superb data set. It's basically showing you the differences in density over an area. Now, I think actually the pitch of this talk is more for geologists who are not comfortable with using geophysics. I think there's probably nothing I'm going to say that a geophysicist doesn't know. But it's always good to think at the beginning, you're looking at the first gravity image that you have, just the Bugey gravity. Basically gravity data that has had the air to surface interface removed or accounted for. And what you're left with are areas that have a high response, indicating that probably the rocks are denser there, and areas that have a lower response, and most likely the rocks there have a lower density, so they're probably more likely to be felsic rather than mafic rocks. So already you can just mentally domain your project area based on the distribution of density. One thing that's always good to keep in mind, and I've made myself a little quick schematic here, this is a cross-section of the Earth. When you're looking at gravity data, you are either looking at a change in density, so you go from a more dense to a less dense body, and here's my not so accurate but close enough gravity profile over this scenario. You can have exactly the same gravity profile resulting from not a different rock type, but a different depth to the top of one single rock type. So this is the scenario where you've got a faulted basement block, and this is the scenario where you've got two different basement blocks. And you can't really tell the difference across your data, but this is a good example of where any control data that you have, it's really important to bring that in and use that when you start to understand your filtered products, and then when you start to go on and do an interpretation. If you have scope, I would always take some rock samples from various parts of your project and send them to Barry's lab, send them to a petrophysics lab. Barry Bourne has one in Perth, fantastic. Send it off there, get to know the densities of your rock units, and then you can answer, pretty early on some pretty fundamental questions about what's happening in your area. A point that is always worth noting. So this data is exactly the same as this data. There's a big difference between data and an image. So generally data is in the form of, when we're at this stage, it's a grid. So a grid actually has real numbers in it, real data values. An image is just a representation of that grid. So you can image your data in the way shown on the screen, where we've got sun shading from the northwest, or you can image your data like this one here, which I think is just from directly above, vertical. Now, some people hate this wet look. I don't mind it. Some people prefer other imaging schemes. Get to know what you like in terms of imaging. There's all sorts of possibilities. But don't forget, don't just use images with one particular sun angle. You're going to miss a lot of detail. All right, so this particular area, that's, well, this is Broken Hill. Yes, good. Okay, Broken Hill is there. And on the right, we've got a little zoom in over Broken Hill. There's the line of load. This is the regional, what state are we in? New South Wales, Geological Survey of New South Wales data, or maybe the GA data, but it's quite regional. Here is an example of an airborne gravity survey, gravity gradiometry survey that was flown. I love airborne gravity gradiometry data. It's fabulous. If you have the opportunity to fly it, do so. It just gives you that detail that you don't get and you wouldn't expect from Australia-wide regional data. And which is something that a lot of people don't realise, but Australia is covered with quite good resolution magnetic data. And that's simply because the airborne magnetic platform was available much earlier. It's much cheaper. Gravity data is just as good, if not better, than magnetic data. It just we haven't had the airborne platform for very long. And it's also still quite expensive because of all the R&D and years spent developing it. So it's just as useful as magnetic data. And if you have the opportunity, please fly it so you can use it and it can be a complementary data set to your magnetics. Okay, the first actual filter. This is just a horizontal gradient filter applied to gravity data. It's about as basic as you get in terms of filtering, but it's just good to pause and think about what we're doing and think about what it's supposed to be showing you, actually what it is showing you. So I think here I've put the state structures, the statewide faults over here. And you can see this big boundary coming down here. If I flick back to the original Bugay gravity data, you can see that boundary. But the purpose of filtering, actually, the main purpose of filtering, it is to make things easier for yourself. You're not filtering just for the sake of it. You're filtering to transform the data into a representation that makes it easy to see the features that you want to see. It makes it easy to pull out where the edges are. Where you've got some weird disjointed zone that may be perspective. You're just turning your data into a representation that is easier to understand. So if we go back to the horizontal gradient, this is an ugly image, but it's also a very powerful image. It allows you to map out all the structures. And it also allows you to see where there's discrepancy between either a previous interpretation or the existing statewide government interp of an area. I think a point worth noting, if you pick up a project anywhere in Australia, you've got access to incredible data in terms of public domain geophysics and interpretations that have been done. But those interpretations are not perfect. They're always ready for refinement any time that you collect more data. And so here, my point was, you can follow this feature down, and around about here, the interpreted line does not agree with the gravity response. So you can ask yourself why. Perhaps that fault is actually offset. Maybe there's a bit of an east-west disruption. Pose a question, try to answer it with the data that you have. Use multiple data sets. Don't just use the gravity, use the magnetics as well. Here's a schematic, and I'm a big fan of these simple schematics. Cordell made this in 1979, and it's still just as valid today. You've got this is a cross-section down here, a dense body of rock, a less dense body of rock. You've got a simple drop-off in your gravity field, that's the blue line, and this green line is your horizontal gradient. So any place across your data where you find a ridge, like a nice traceable horizontal gradient high, that is representing the edge of a gravity unit. And so that might be a really important fault. So it may be a pathway for fluids, mineralized fluids, or it may be the difference between one unit and another. But even that unit change is pretty important to know. So take your time, look at the data, map out these edges. The way you calculate edges from gravity and magnetic data, you can do it in a number of different ways. This is the standard horizontal gradient way. All right, you can look at this in your own time. Move on. Tilt angle filter. It's a nice little complement to the horizontal gradient. It's extremely busy, this filter. And I would not use the tilt angle filter until you've familiarized yourself with the data and you're quite comfortable with what's going on. Up here, I've made another one of my rough and ready schematics, but I think it's worth just having an idea in mind in terms of what this filter is showing you. So once again, it's a cross section. We've got a body that comes quite close to surface, and it has quite a strong gravity response. We've got a deeper body, same contrast, but anytime a body is deeper, it's further away from the source, the amplitude of the response is going to be lower. So you can see that's the responsive body here. And here we've got a shallow but depth limited body, and you still see it, but it's not as strong because of the limited depth. The point being the tilt angle, it's just a crude, brutal filter. You're either on or you're off. And so in a way, it's really good is to domain your data into on and off. Either there is a mag response or there's not. And so you can map out texture, you can map out structure, you can do all sorts of things with the tilt angle. But it's very busy. It's not what you would use when you're starting out in terms of your interpretation and your understanding. Once again, this data is exactly the same as this data. It's just a different imaging scheme. And you can see here the little inset that I've put in top right. This is the original Bugay. And that little inset sits in this white box here. You can see with the tilt angle, you can define breaks. And I think there's probably a big fault running through there. See it really well in the tilt angle. And if you go back to the original Bugay, you're really going to be forced to work a lot harder than you really need to if you don't use the filtered products. All right, your classic first vertical derivative. I think everyone is very familiar with this. I got a little bit excited and put in the transfer function. I was going to explain how filtering works in the frequency domain. I'm going to do it quickly. Actually, I'm just going to leave that because we probably should just look at data. But the first vertical derivative, basically, it just keeps the high frequency. So the busy part of the signal, it enhances noise, but it's a really powerful filter to just show you all the detail, what is happening, what are the responses close to surface, what can I see in the data? It's ugly when you apply it to a lot of the public domain data simply because there's variable resolutions. And here you can see that on the South Australian side, the spatial resolution, so the distance between stations is much smaller. And over here you can see that actually the distance between stations is quite coarse. So you've always got differences in resolution. What you can do is just apply a nice Gaussian smoothing filter, but I always think you should have a set of filtered products that are not smoothed. It's so easy to clean up geophysical data and make it look pretty, and then as a result you lose a lot of your ability to apply you can mentally apply a bit of a confidence filter when you use data that hasn't been overly smoothed. Like down here, you go, okay, I don't think there's a lot of data supporting what's happening down there. And likewise, top right looks a bit low in gravity stations. But once you smooth the data, it's very hard to tell where you've got problems and where you don't. So yes, the Gaussian smoothing filter is like a youth filter for geophysics. When I put this together, I was in a funny mood. So use it if you're giving a presentation, sure. Use your products that have had the nice smoothing filter applied, but make sure you look at the raw data as well, unsmoothed. One thing that you can do with gravity and magnetic data, and you can and should always do this, is you can separate responses, not in any perfect setting, but you can do a good job, do the best you can to separate responses that are shallow and responses that are sort of intermediate and responses that are deep. Now, there is no perfect way to separate the responses, and certainly the degree to which that works depends on the nature of the geology. But I always say, give it a go and at least give yourself 3 separate products that are the high frequency, the intermediate, and the low frequency, so that you can build up your understanding of the area. And it is actually a really useful way to interpret. Look at the deeper responses and domain, work out where your broad units are, and then gradually come up and get up to the detailed response. And the shallow residual data can often show you where along a key structure you might have some serious discontinuity, or just localized structural complexity that you wouldn't necessarily see if you hadn't filtered the data. Same area, magnetic data. Look how detailed that is, only because it's been flown at a much higher resolution. It is beautiful data, and you can see a lot in there. I think we're going to, what did I put in here? We're just going to whiz through a few different filters. This is just the reduced to the pole magnetics, and it is worth, move the heads around. It is worth just looking at this little schematic. I don't find very many people who still interpret off TMI data, but just to stress, you must always interpret off your reduced to the pole magnetic data. There's a good reason for that. The reduction to the pole transform, it shifts your magnetic response to be, it shows you the magnetic response as though your inducing field is vertical. So it simplifies the magnetic response. If your body is still inclined, so it has a dip, you're still going to see asymmetry in the response, but you're not trying to work out in your mind with an inclined field where the feature or the body is relative to the response. So always reduce your data to the pole. If you're near the equator, that can be troublesome. There's different approaches to that. Actually, there's an approach that Ian Stewart has wrote a paper on, and it's actually a really good approach. You can do your RTP in various stages. Anyway, that's probably something to get a geophysicist to do for you. What have we got here? We've got shallow residual. Okay. So remember I said you can separate your data into shallow, intermediate, and deep responses. So here we've got the magnetic data over the Broken Hill area, and we've just kept the 0 to 50 shallow residual. So all I've done to the data is I've taken the original RTP, the original data, I've upward continued that data 50 meters. And so what that means is I've just calculated, because we know the properties of this lovely 3-dimensional magnetic field, we can work out what the response looks like when we move above the ground, and we can actually work out the response anywhere. Quite wonderful. But in this particular case, we've just upward continued 50 meters and we've subtracted one from the other. So you're just retaining the very high frequency signal. There is no meaning in those numbers. In a perfect theoretical world, that would be the top 25 meters of the Earth. It is not true. Don't even think about it in terms of depth. Just think of it in terms of frequency. We are keeping the busiest part of the signal, and that allows us to map out all the detail, which is what we often want for mineral exploration. See a bit of culture there. Nothing's ever rectangular like that. You can also see a bit of noise. Any of those, I suppose, any filters that require the use of first or second order derivatives are always going to include some noise. We can then move down to lower or longer wavelength responses. And as we do so, we can map out the broader units in the area. This is what I call the res combo, but all it is, it's a way to represent your data that anyone can do. Actually, probably we are most familiar with ternary representations of geophysical data when we look at radiometric data. So often with radiometric data, we combine potassium, thorium, and uranium into a ternary display. So we assign potassium to the red channel, thorium to the green, and uranium to the blue. There's no reason we can't do that for potential field data, so for gravity and magnetic data. And what I do regularly, and I really like this display, is rather than the different radiometric elements into the red, green, and blue, you put the shallow, intermediate, and deep residual filtered RTP grids in there. And you just get this nice amplitude, subdued, lovely view of the subsurface that I find really calming for interpretation and for seeing structure and patterns and texture and the like. And one thing that is important with, once you go on to do your interpretation, you need to use multiple products. There's no perfect filter. I always recommend to clients that you choose maybe just 10 products that you find useful. And how do you define useful? When you look at existing data, so you look at drilling, you look at local geological knowledge, which products best represent hard data? Like which products are showing you structures that you know to exist? Which products are highlighting a known occurrence in the area? Subset your products into maybe 10 and then go for it. Just interpret it as at will. Move along. Yes, my point being, choose several products, look at them together, click them on and off using whatever GIS package you're using, and start to recognize patterns and the character of units. You can see this particular unit up here as it goes undercover. I think it gets, actually the frequency is similar, but it loses its amplitude. So in some filtered products, you can see it well and you can track it. For example, the tilt angle in the middle. And in other products, you just can't track it very well. Remember, the tilt angle was that filter that it turns the data, I'm giving it, gives the data on, makes the data on or off. So once you've got your eye into the area, you can use that and interpret. The analytic signal is quite an important filter, and that's shown on the left here. It often gets a bad rap because it's quite a noise enhancing filter because you're using 3 of the derivatives of the field, but it's a really useful filter for seeing where you may have remnants. So what is remnants? Some magnetic bodies have their own inbuilt magnetic field, and they hold on to that, and that really distorts the signature that we measure when we fly over them. The analytic signal is a filter that has very low sensitivity to that remnant. So if you have a high in the analytic signal, it's more likely that where that high is the location of the body. So you can compare your analytic signal to your first vertical derivative and just see where there are changes. It's often very powerful for mapping discrete intrusions that may have a remnant part. Or sometimes, if you've got intrusions with multiple phases, some phases are remnant, some are not. Yes, it's quite a powerful tool. Okay, we're going somewhere else now. I can't remember what's next, but we're going here. I think this is actually Victoria. There's a point I wanted to make here. So we're looking at gravity data again. On the left is gravity data with vertical illumination. So we're highlighting the data from above. And on the right, we've got shading from the northwest. And you can see that the images are quite different. So remember to always use multiple images. Don't just interpret using one illumination direction. The point I wanted to make here, and I've already made the point, but I hadn't shown you actual data points. So this is, on the left, the black dots are the actual gravity stations, and I think we are in Victoria. So you can see on the right, this area up here, you wouldn't necessarily immediately recognize it as an area with basically no data, because the gridding and the smoothing and the filtering, it works well to present the data in a nice light. But as you can see, there is actually no data in there supporting what is happening in there. So you could have a discrete gravity high that you just don't see at all. Point being, always use the station layer as well as any filtered products that you've been given to interpret your data. And all you need to do, there's no issue there, you just need to assign a lower confidence to that particular area. And so any interpretation and any targeting methodology would have a high uncertainty assigned to that particular area. Okay, now we're up in the Patterson. We're just going to whiz through some data at the same time.
We've probably got about 5 minutes left, Amanda.
Okay, thanks, Helen.
All right.
We're just going to look at Havieron. Havieron sits here in the gravity data. So on the left is the original Bugey gravity, and on the right is a shallowish residual. And you can see this big unit up here just to the east of Winu. There's a lot of character that comes out once you apply your residual. Why would you force yourself to interpret here when you don't get, you really can't see what's going on, because you've got the underlying response as well as the shallow response. So always filter your data to give yourself a good chance of mapping things well. Here is Havieron. It's a nice discrete mag lip sitting on this northwest structure in its own unit. I think it's just a perfect geophysical case study. Discrete mag high, but let's just move through. So you can hardly see anything out here. These units do not have much of a we're looking at mag now, magnetic response at all. But as you filter your data, you can start to pull out character in the units to the east. Is that character important for finding a mineral deposit? I don't know. And it's the point being, you can push your data quite far and propose some ideas, and then really get to know what's happening. Shallow residual, Havieron stands out nicely. Not much happening over to the east. This is another filter that I always run, and it's really useful. You just take the vertical derivative and take the horizontal gradient, subtract one from the other, and you're left with this pseudo detailed mag data on steroids view of the Earth. It's really good for clearly defining any linear units and obviously discrete mag highs. The tilt, what's happening in the tilt? I've got another case study, but I might just leave that in the I'll just see if there's anything I wanted to actually. Oh, this is worth just looking at in my last minute. I mentioned to you that you shouldn't interpret RTP data, and so this is just a schematic. This is a cross section. This is a magnetic body, and this is the total magnetic intensity when the inducing field is not vertical. And so how would you interpret that? You'd put a body here, there's a low, you would just make a complete mess of it. So you reduce it to the pole, you've got a nice high over your body. Simple, easy to interpret. Don't make life difficult for yourself. One thing that I often read in reports that's simply not true. When you reduce your data to the pole, you're not removing the dipolar field. You've still got a positive and negative pole, but you're just taking your readings, let's say at the North Pole. So the geometry is simplified. If your body is depth limited, you're still going to get these negative loads due to the negative pole as well. The only way you remove the dipolar field is when you run what's called a pseudo-gravity transform. And unfortunately, I don't have time to talk about that. Last minute, Helen hasn't stopped me. Always be aware In government merged data, we are very lucky to have the data, but always put on the registered survey layer so you can see where the survey boundaries are. You don't want to interpret an increase in basin fill that actually is just a survey boundary that has been merged well. So use the data, use the supporting layers that you have well, both in terms of surveys that are contributed to the compilation and the gravity, the actual data points, so that you know which areas to assign a higher level of uncertainty.